Hi everyone, myself Dr. Lakshmi Prasad, working as a professor in CSC, working in Institute of Aeronautical Engineering, Hyderabad. In this video, I am going to discuss about graph coloring. So before going to see that, so what is a graph theory? So it should be a branch of mathematics, so concerned with networks of points connected by lines. And the subject of graph theory has its beginnings with the recreational math problems, and mainly it is going to be used in mathematical research, so with various applications in chemistry, operational research, social sciences, and computer science. And this history of this graph theory may be specifically traced, and which is going to be solved the problem like cosine bridge problem, so should be done by Euler. And so this should be the problem of cosine bridge problem. So this should be a puzzle concerning with the possibility of finding a path over 7 bridges that span a river flowing past an island. So, but without crossing any bridge twice. So for that problem, so we are going to be designed in the form of a graph theory, and this problem is going to solve by the Euler. So this should be the city here, and where the river is floating across various parts of that, and how can able to solve this one. So in elementary mathematics, so the term graph refers to a function graph, or it should be a function that is going to be plot. And as used in graph theory, so the term graph does not refer to any data charts like a line graph or bar graph. So instead it is going to be referred to a set of vertices, so that should be treated as a points or nodes, and edges that should be connected with the vertices. So these edges is going to consider as lines. And simply I can able to say that the graph should be a visual representation of edges and vertices, and edge is nothing but a line between the two boundaries, and vertex is nothing but a point where two lines meet here. So in elementary graph, so the graph is nothing but a function, or it may be a plot, I think. And the term is the graph does not refers to data charts like a line graph and bar graph. So for that, we are going to treat this point. So what is there in this one, the plane? So these and all will be considered as nodes here, and these nodes are going to be joined by a line or edge. So these lines are going to be called as a vertices, and this one will be called as edges. So the graph is nothing but a collection of vertices and then edges, and so the edge is nothing but a line which is going to be joined the two vertices, and vertex is nothing but a point, or it may be a node, so where the line is going to be joined. And this should be the representation of edges and then vertices. So if I'm going to consider this, and this part will be considered as the vertices, and this and the lines what is going to join the points should be treated as an edge here. And comes to types of graphs, so we're going to have different kinds of graphs like multigraph, so where the multiple edges are going to be allowed between the vertices. And simple graph means that a graph which is not going to maintain any loops, and at most one edge is going to maintain between the two vertices, then I can able to say that should be a simple graph. And the pseudo graph is nothing but a graph that may contain multiple edges and graph loops. So let us consider this a simple graph. So a simple graph is the graph which is not containing any multiple edges and self loops. So then I can able to say they should be the simple graph. and this should be one of that. And multiple graph means that, so if I'm going to maintain the multiple edges in between them, then I can able to say there should be a multi-graph. And if I'm going to consider a graph which is going to maintain the multiple edges and then self-hoods as well, then I can able to say there should be a pseudo graph. Okay, like this we are going to be constructed different kinds of graphs here, and for solving any kind of application. So normally a simple graph in terms of vertices and edges. So if I'm going to draw any arrows or weights in between them, there should be unlabeled graph or simple graph. So whenever the edges is going to have maintain the weights, and they should be called as a weighted graph. And if I'm going to maintain the vertices, then I can able to call it as a directed graph and undirected graph. So here in this diagram, so whenever the graph is not going to maintain any kind of indications between them, then I can able to say they should be unlabeled graph. And here, so whenever the edges is going to be labeled with number, then what we call it as edge labeled graph. Whenever the vertices is going to have the indications of numbering or whatever the characters like this, then I can able to say they should be the vertex labeled graph. So normally you are going to have different types of graphs as well, like undirected graph. So that means where the edges is not going to maintain any kind of directions. And similarly, if I'm going to draw, whenever the edges is going to have the directions, so then I can able to say they should be a directed graph, right? And suppose if the weights are going to have some have in the edges, then I can able to say they should be weighted undirected graph. And similarly, if I'm going to draw any lines in between them along the directions, the edges is going to maintain the weights, then I can able to say they should be undirected weighted graph. So like this, we are going to have different kinds of graphs as well. So next we are going to see what should be the graph coloring. So the graph coloring is nothing but the assignment of labels or colors to the edges or the vertices of the graph. So most common types of graph coloring is that two types. So first one is that edge coloring and second one is that vertex coloring. So what is this edge coloring? So edge coloring is nothing but so the assignment of labels or colors to each edge of the graph such that no two colors is coincide with the adjacent edges. That means, so whenever I'm going to have assign a color to the edges of the graph in such that they should be blue, and next color what I'm going to say that should be red, then only I can able to say this should be edge coloring. So the no two edges we should have same colors with coincide with each other. And the vertex coloring also same thing. So here we're going to make an assignment of labels or colors to each vertex of the graph such that no two edges going to connect the two identical colored vertices. So that should be called as the vertex coloring. So the graph coloring will be of two categories. So first one is the vertex coloring and then edge coloring. So what is this vertex coloring means that, so if I'm going to consider a graph here, so if the graph is going to be dark with some color like red, so the next color should be some other color that should be blue. So next thing, so if I'm going to map with another color like red, so these two adjacent vertices not coincide. That's why this one what we called as a vertex color. Suppose if I'm going to have the red, so the two vertices are going to be coincide with each other. So I'm not going to apply red in this case. So for that, what I'm going to I have to apply another color blue. So if I'm going to see like this, so no two vertices are going to be coincide with each other. So that's why what we call this as vertex coloring. So similarly in this case, so if I'm going to draw with edge with red and this one as blue, and similarly what kind of color I can able to apply, that I can able to apply green as well, and this should be yellow. So this should be what we call as edge coloring. So in this case, I have considered four colors. So instead of four colors, what should be the minimum coloring is going to be applied for the edge is also one of the case we have to consider. So for that, what we call as a chromatic number is there. So based on the vertices, what common number of minimum colors that are required for edge coloring and vertex coloring is going to be considered. So see the examples like a vertex color graph. So we are going to have four vertices. So I'm going to have different colors of the vertices and edge coloring. So if I look at this edge coloring, so this is one red, green, yellow, and then blue. And here also the vertex as well as edge both are applied to the graph. So then how the graph looks like this. So one of the reasons that the graph coloring means that the subfield of the graph theory become its own branch of maps, that should be called as well-known four color problem. So this should be the four color problem. So it is going to be says that any map in a plane can be colored with using four colors in such a way that the regions is going to be share a common boundary, does not share the same color. So that should be the four color problem. So whatever the graph is there, so that should be maximum we can able to apply the four colors. So with this four colors, we can able to solve the problem in such a way that the no two nodes or points will not share the same color. So normally, what is this coloring? So coloring is nothing but is the assignment of colors or any distinct marks to the vertices of the graph. And strictly speaking, that the coloring is a proper coloring if no two adjacent should have the same color. So if I'm going to consider a graph like this, so in this graph, what I'm going to say that, so if I'm going to consider a graph like this, like nodes, and then I can able to have another color, and I'm going to apply like this. So different coloring is applied here to the vertex of the graph. So in this case, what I'm going to say that is, uh, so no, how what is the minimum color that is required to apply for the graph is that we have to be considered. And coloring planar graphs. So a graph is said to be planar if it can be drawn in plane without edge crossings. Okay. So what is this definition is that, so a graph is said to be planar. So if I'm going to draw it in a plane without edge crossing. So there are going to have two types of graph. Previously what I said should be directed graph and undirected graph and weighted graph. So these and all three other kind of the graph what I'm going to discuss is that planar graphs and non-planar graphs. So what is this planar graph or non-planar graph? So whenever the graph is drawn in a plane in such a way that the edges should not be coincide or cross with each other. So this should be a planar graph. So whenever the edges are going to be crossing with each other, then I can able to say this should be a non-planar graph. So that is the only indication. So the edges should not be crossed with each other. Then it should be a planar graph. Whenever the edges is going to be crossed with each other, then I can able to say they should not be a planar. So normally this four color theorem is going to be applied for every planar graph only with the chromatic number less than or equal to 4. So just now I said that so any kind of graph I can able to apply the four color theorem such that so minimum of at most four colors are needed to color any kind of the graph. So but according to four color theorem that should be applicable only for the planar graph. And so that was posted in conjecture in 1815 itself and then finally proved in 1976 after hacking by the aid of the company. So sometimes this graph coloring, what I said, that should be assignment of colors and assignment of colors to the vertices as well as edge, and this should be considered as NP complete problem or PQ problem as well. So how many colors that are required for mapping a turquoise, I want to know. So for that, what I have to say that is this should be a problem of NP complete. So coloring is a proper coloring such that the no two adjacent should have the same color. So if I'm going to consider one of the applications, right, how many colors that are needed for turquoise map, so how do we find it out? So similarly, next concept is that edge coloring. So what is this edge coloring? So for the given graph, if I'm going to color the edges, I can able to say that the node two vertices is going to have the same color. So if I'm going to consider another graph, so for this graph, how many colors are needed for coloring the vertices of this graph? So let it be red, and this is considered as blue. And similarly, what is the under color? What I can able to fill here is that if I'm going to apply red, no coincide. So for this one, so red is not going to be applied, and blue also not going to be applied here. So that's why I'm going to take another color. Let it be green. So green I'm going to consider, and if I'm going to apply the red, so no two colors is coincide, right? So what kind of color can I able to apply here is red. So here I'm going to apply blue, and red is completed. So I can able to apply green here in this case, and for here blue I'm going to apply, and in this case I'm going to apply red again. So if you look at this, the vertices of the graph, no two edges are going to share the same color. So that should be the problem of edge coloring. So for the given graph, so we can able to color the edges that such that no two no two vertices is going to have the same color. So normally this edge coloring problem can be formulated from vertex coloring problem only. So let if L of J should be the auxiliary graph and G can be the graph for when we are going to try to color. So the L of G means contains the vertex for every edge in the graph G, and there is an edge in the L of G going to drawn between these two vertices if their associated edges in the graph should be share a common vertex. So auxiliary graph, what should be the similarity of the same graph? So normally this edge coloring is going to be formulated from vertex coloring only. So whenever I'm going to consider an auxiliary graph, so the auxiliary graph is almost similar to this the input graph. So where the edges and then where the edges almost all same in the graph here, which should be the copy of that graph. So what is this four color theorem? So this four color theorem is going to states that the planar uh, map can be colored with at most four colors. So in graph terminology, if I want to say that is, so at most four colors is going to be required for coloring any graph, such that the node should be colored and the no adjacent nodes should have the same color. So normally this should be invented by Francis Guthrie in 1852, and many incomplete proofs are available. Five color theorem, and then finally this four column theorem is proved in 1977 with major computer based proof. So the four color theorem is going to say that in any planar map can be colored with at most at most four colors, and this means that at most as four colors is sufficient for any kind of graph, such that no two adjacent nodes should have the same color. So the vertex coloring, just now what I said is the vertex coloring should be the assignment of colors to each vertex of the graph, such that no edges is going to be connects two identical color vertices. So if I'm going to consider a graph here, so I'm going to have blue. So next I'm going to apply green. So again apply blue, green, blue. And if I'm going to apply green here, then definitely I have to change it with some other color. So what I'm going to say, that should be orange, and middle of that should be red. So if I'm going to see this, so how many colors I used in this graph is 4. So in this graph I use 2 colors, and if the graph looks like this, so first I have to fill with red color, and I have to check what is the next color I'm going to fill. So that should be green I applied, and next blue I'm going to consider, and here also I'm going to consider green. So like this I'm going to fill all the vertices of this graph. So at most how many colors are needed in this case? So red, blue, and then green. So 3 in this case. So suppose if I'm going to have another different kind of graph, so how many colors are needed in this one? So here also 3. So like this, if I'm going to consider any kind of graph, so the 4 color theorem is the only solution to the problem of coloring graph. So in this one, what I'm going to say that is vertex coloring is an assignment of labels or colors to each vertex of the graph, such that no two edges is going to be colored with the same. And next one is that edge coloring. So edge coloring is nothing but it should be similar to the vertex coloring. So except it should be edges are going to be colored. So in this case, the adjacent edges is going to have different colors. Okay. So how this vertex coloring is done in similar fashion, we can able to do the edge coloring also. So the adjacent edges is going to have different colors. Okay. So in what way I can able to apply this in similar fashion, you can able to do that. So if I'm going to consider this graph, so I have to apply one color each in the same similar fashion. Then I can able to check whether any two edges are going to be coincide with each other or not. I have to check it out each and every edge of the graph. So every edge color problem can be transformed into vertex color problem in such a way that the colors of the edges should be same as the color of the vertices. So not every vertex color can be transformed to the edge coloring, and every graph should have the line graph, but not every graph in a line graph of some other graph. So this edge coloring problem can be transformed into vertex coloring problem, and the coloring of edges of the graph is almost similar to the color the vertices in the graph as well. So not every vertex color problem can be transformed and then into edge coloring. So that should not be. Vice versa is not possible in this case. And whenever every graph is going to have a line graph, so not every graph in line graphs have. So next one is K coloring. So what is this K coloring of the graph? So the K coloring of the graph is the mapping of vertices on the integers of 1 to K such that the adjacent vertices are mapped into different integers. So the K coloring partitions should be the K disjoint subsets such that the vertices from the different subsets have different colors. Okay, so the K coloring of the graph should be the mapping of vertices of the graph with the numbers like 1 to K such that no adjacent vertices should have same color, that should be different integers. So the K coloring partitions can be done into K disjoint subsets, and then such vertices should be different from different kind of terminology. You are going to see that is K colorable. So that means a graph is a K colorable if it is have K coloring. And next terminology is chromatic number. So chromatic number is nothing but the smallest integer K, and for the graph G is the K colorable, that is called chromatic number of the graph, and that should be denoted by like this. So whenever a graph is going to be drawn, so the problem is that what is the minimum color that is going to be required? What is the minimum color that is going to be required to color the graph? So that's for that we are going to have the chromatic number. So there should be the smallest integer value for the graph which is going to be colorable. That one what we called as chromatic number, that should be given. And next, what is this NP hot problem? So the NP hot problem is nothing but there should be a class of decision problems. So that is going to be solved in polynomial time or non-deterministic machine or with a non-deterministic algorithm. Okay, so NP means that we should be a class of decision problems. So that should be solvable in polynomial time with the non-deterministic machine like non-deterministic algorithm. And deterministic, you know that. So non-deterministic computer means is the one that where can able to guess the right answer or can able to guess the solution with the non-deterministic algorithm. So it should be frequently spam and infinite number of the process. So thus the NP can also be thought of class of problems whose solutions can be solved in the polynomial time. So the NP problem can be a thought of a class of problems whose solutions can be solved in the polynomial time. So that NP stands for itself a non-deterministic polynomial time. So the NP hot problem is nothing but a class of problems so which is going to be solved in polynomial time with the non-deterministic algorithm, and this non-deterministic computer is the one where we can able to guess the right answer or the solution of non-deterministic computer. And here there should be the class of problems which is going to be solved polynomial time with non-deterministic. So some of these NP hard problems like fractional absorb, sorting, and graph coloring should also one of the problem of this. And satisfiability, the problem of deciding whether the given Boolean formula is satisfiable or not, that should be the satisfactory. So these are the class of problems that should be comes under NP hard. So first one is fractional knapsack. So knapsack is the problem where the thief is going to be fill the items into his knapsack, that is nothing but a bag. What is the maximum profit he can able to obtain, and then sorting is also NP hard problem, and graph coloring satisfiability also. So what are the applications of graph coloring? So many problems can be formulated as graph coloring problem. So including the timetable, scheduling, register allocation, channel assignment, like this. So many problems are going to solve through graph coloring only. So like timetabling and then scheduling and then register allocation, channel assignment. So a lot of research also going to be done in this area. So which one is already known about the problem space of this. So this should be one of the problem where you can able to apply the graph coloring. So mapping this different colors of the states of India, so that it can able to solve through the graph coloring problem only. So the standard approach of coloring the graph is to use a single color for the state and never use the same color for these two states. So such that no two colors should be able to shade the two states of this India. So the two states which should be the common point should be colored. So where also done through the edge coloring also. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.